We have talked about gets, bras, and operators. In this class, we'll see how we can represent this as matrices. So far, we have talked about gets, bras, operators, etc. All right, as part of the mathematical formulation of quantum mechanics. But these objects are rather abstract, and it's not clear as to how we can extract some useful information from these things. It's not clear how we can, extract some numbers from these abstract objects. Right? So whenever we make a prediction about a physical system, we need numbers. Right? So how can we extract something like that from these objects? So here we'll see, in this class we'll see that there are various ways of concretely representing these objects. Okay, we'll talk about representing these objects by matrices. We'll see that gets can be represented by column matrices, bras can be represented by some sort of a row matrix, and operators by a square matrix. Okay, square matrix. This has n rows and this has n columns, etc. Okay. Now, whenever we talked about operators and gets and bras, we actually gave examples from matrices, from matrix algebra. Okay. Now, in this class, probably you'll understand why these examples worked. Okay. Let's talk about the two-dimensional Euclidean vector space for a moment. Okay. So suppose we have this two-dimensional Euclidean vector space. In order to do something useful, we usually take a coordinate system. We usually choose a coordinate system, and the unit vectors along the coordinate axis can be chosen as the base vectors. Okay, these are called the base vectors, E1 hat and E2 hat. Sometimes we write as I hat and J hat. Okay, here we are using the notation. We are writing the same things as E1 vector and E2 vector, E1 vector hat and E2 vector hat. All right. Now suppose we have got a vector in this space, V vector. Right. Now, once we have a coordinate system, we can decompose this vector into components along the coordinate axis or along the base vectors. Sorry, along the base vectors. Here, base vectors are E1 hat and E2 hat. Right. So basically, we can write V vector is equal to V1 E1 hat plus V2 E2 hat. This V1 is called the component of V vector along E1 hat direction, and V2 is called the component of V vector along E2 hat direction. All right. But now once we have chosen the base vector, so once we have chosen the coordinate system, we can simply represent every vector by simply by simply giving these numbers. Right. If I give these two numbers, then the vector is completely specified. All right. If you remember, we have given this definition for vector as a collection of numbers which transform in a particular way. All right. So this actually should be thought of as a representation of the vector. The vector can be represented by two numbers in a two-dimensional Euclidean vector space. Right. So once we choose the coordinate axis, or once we choose the coordinate system, or once we choose the base vectors, right. So we can choose the base vectors in the beginning of the problem, and then these vectors can be represented by simply giving these two numbers. In fact, we can write these two numbers as a column matrix. All right. So in this case, we can say that the vector is actually represented by, this symbol will be used to mean represented by. Okay. Represented by. So the vector can be represented by a column matrix. All right. So once we have chosen the base vectors, we don't have to write these base vectors everywhere. All right. We can simply write this thing as a column matrix. Okay. So the vector is represented by a column matrix. Now we could choose some other coordinate axis. All right. Instead of E1 hat and E2 hat, we could choose, let's say, E1. This direction can be written as E1 prime hat, and an orthogonal direction E2 prime hat. All right. Maybe this is a bit crowded here. Let me put it here. We have got E1 hat, E2 hat. This is one choice of base vectors. We could also choose E1 hat prime and E2 hat prime as the base vectors. All right. Again, we'll have these vectors, this vector V vector. All right. Now the V vector can be decomposed into components either in the first base set or in the second base set. All right. So we could write V vector equally well as V vector is equal to V1 prime E1 hat prime plus V2 prime E2 hat prime. All right. So by the choice, by the choice of base vectors, we can, by different choice of base vectors, we can represent the same vector differently. It's the same vector that we are representing in two different base vectors, all right, or in two different base sets, or in two different coordinate systems. And we know that these numbers v1 prime and v2 prime are related to the numbers v1, v2 by a particular kind of transformation. We called it as rotation, right? And if these numbers transforms in a particular way under rotation, then we said that we can call these numbers as vectors. Right? These are some things that we have already seen. The basic idea here is that I want you to take forward is that once we choose the base, gets or base vectors, sorry, once we choose the base vectors, we can represent various objects using numbers, using a collection of numbers. All right. In much the same way, we'll see that in linear vector space or in complex vector space that we have been talking about, various objects can be represented using collection of numbers. All right, using collection of numbers. First, let's talk about the representation of an operator. First, let's talk about the representation of an operator. So having specified the base gets, we now show how to represent an operator, say x, by a square matrix. All right. So what we are going to see is that an operator can be represented by a square matrix. So a square matrix is a collection of numbers. So basically, we are going to represent the operator by a collection of numbers. Okay. Now the base kits, we talked about these base kits, and in quantum mechanics, the base kits of interest are eigenkets of Hermitian operators. So the base kits that we will be using throughout the course will be the eigenkets of some Hermitian operator. So we have the base kits. Now once we choose the base kits, all right, once we choose, let's say, a particular set of eigenkets as the base set, let's say that these are the base vectors. All right. The next question is, how can we represent these objects in this basis? Okay, how can we represent these objects in this basis? All right. So let's see how we can do this. So we had said that the eigenkets of a Hermitian operator forms a complete set, and we had the completeness relation written like this: sum over a prime, ket a prime, bra a prime is equal to the identity operator. Okay, sorry, we didn't have the hat there. This is the identity operator. This is called the completeness relation or closure relation. We said that this expression of identity operator is extremely important. Okay, we'll be using it over and over again. So whenever we are stuck with something, right, whenever we don't know what to do, we just multiply by an identity operator. We just multiply by a 1. All right, and from this maybe we can do something and get something useful out of it. For example, let's say that we have an operator x. Right, let's say that we have an operator x. Right, now as such, this doesn't give us any useful information. It's just an operator sitting there. All right, so since we don't know what to do with this operator, let's just multiply by a 1 on both sides. Okay, by 1 I mean an identity operator. Let's just multiply by an identity operator on both sides. Okay, because multiplying by an identity operator does not change it. It's an identity operator. Okay, so this is identity operator, x identity operator. Now I can write this identity operator using the completeness relation of the base kits. Okay, so I can write this as sum over a double prime, ket a double prime, bra a double prime. What is this? This is the identity operator. Okay, I have used this a double prime as the summation index. Now I have written this first identity operator here. I have done nothing more than writing the first identity operator here. Okay, the x is sitting there. Now I can also introduce a second identity operator, sum over a prime, ket a prime, bra a prime. All right. Now, since I have used this index a double prime here, I should use a different index here. That's why I have used sum over a prime. All right. Okay. Now I can write this as, this can be written as, let me write the summations together outside, sum over a double prime and sum over a prime. Okay. Let me write the other terms together. This is ket a double prime, bra a double prime, x, ket a prime, bra a prime. All right. Now we see that by the associative axiom, we can combine these things. All right. Because as long as this multiplication is legal, we know that this multiplication is legal. So we are allowed to combine these terms. This was the associative axiom. All right. And we see that if we combine these things, this is a number. This is a number because x acting on ket a prime will give you another ket, and then you are multiplying a ket and a bra, which is a bracket, and it's a number. So since this is a number, it doesn't matter where you put it. You could put it to the right of a ket or left of a ket, doesn't matter where. Okay, so let me take this number to the left of this thing. Now I am writing, remember I started with this x. Okay, so now I can write x equal to sum over a double prime, sum over a prime. Okay, and I have here a double prime, bra a double prime, x ket a prime. Okay, since the following multiplication may not be legal, I'll be on the safe side and write a bracket here and a dot. All right, what do I have left here? I just took this number to the left side. All right, I have this ket a double prime there and this bra a prime here. Right, now you see that this object, right, this object is constructed out of the base vectors. So once we specify the base vectors, we can construct objects like this by combining different bras and kets. Okay, different kets and bras. Right, so this is part of this object. We know it's part of the specification of the base vectors. Okay, we can construct it from the base vectors. We see that whatever appears here, it's a number. It is a number. All right. So how many numbers are there? There are n square numbers of this type. There are n square numbers of this type. Okay. So basically we are expanding the operator. We are basically expanding the operator, or we are writing the operator as a sum of different operators. All right. So this is an operator. So we are writing the operator as a sum of different operators. All right. So this is what we have done. And when you combine different operators, there are some expansion coefficients. Right? Now these expansion coefficients, there are n square of them, and then you can write this as a square matrix, and we can call this as the representation of operator x in the basis ket a prime. Okay, hope this is clear. So let's look at this number again. Let's look at this number again. All right, this is part of the this is obtained by specifying the base kets. All right, so let's look at this number. Bra a double prime x ket a prime. Now, if you are talking about an n-dimensional space, then there are n base kets. There are n base kets, a prime, a double prime, goes on like that. And how many are there? There are n of them, right? So since there are n of them, there are n base kets. There are also n eigenbras. Okay, there are n eigenkets. There are also n eigenbras. Bra a prime, bra a double prime, etc. All right. Now, each one of this can be combined with all of this. Right. So each one of this can be combined with n of this. Right. The second one also can be combined with n of this. So in total, there are n square such numbers. There are n square such numbers. Okay. How do we construct these numbers? You pick a bra from this set, write x, and then you pick a ket from this set. All right. And then you can construct n square such numbers. Okay, n is the dimensionality of the ket space. Now we may arrange this n square numbers. All right, this n square numbers can be arranged as an n by n square matrix, such that the column and row indices appear as follows. Sorry, this is the row index. You can call this as the row index and this as the column index. All right, you see that there are n square matrix elements like this. Okay, if this is the row index, for example, the matrix would look something like this. Okay, we would have some this is bra a double prime x a prime. Okay, maybe I should so in order to enumerate it easily, maybe I should write it using the second notation that we introduced. I'll write this like this. Let's say we have got a bra a1. Okay, we have got bra a1 x ket a1. Right, so this is the 1 1 element of this matrix. Okay, 1 1 element of this matrix. Right, so it's the first row, first column. What would be the second entry to this matrix? You will have the first row, second column. So this would be a2 x. Sorry, this is first row, so this is a1 x a2, like that. All right, and here this is the second row, so the row index will say this is a2 x a1. Okay, so this index will tell me which column I am in, and this index will tell me which row I am in. Right, so I can construct an n by n. So this can be considered as the elements of an n by n square matrix. All right. Now we can write the matrix explicitly like this. X is represented by, so this means that the operator X, this symbol stands for is represented by, okay, this matrix. The matrix elements are A1 x A1, A1 x A2, etc. We do not use the equality sign here because the particular form of a matrix representation depends on the particular choice of base gets used. Right, so this matrix looks entirely different in some other bases. Okay, here let's say that we have chosen the eigenkets of an operator A as base gets. Okay, the eigenkets of an operator A as base gets. Okay, we denoted it like this. So A is a Hermitian operator, and we could choose some other Hermitian operator B, okay, whose eigenkets are denoted by ket B prime. Okay, this is a set of eigenkets. Now, in this basis, the matrix elements would be B1 x B1, okay, B1 x B2, etc. Okay, and these matrix elements are completely different. These two matrices would represent the same operator, but the matrix elements are different. Okay, so the matrix looks different based on the basis that you choose. Right? So this is the reason why we should be careful. X is represented by. We say X is represented by. We don't say X is equal to. All right. But in some textbooks, we'll still use X is equal to. We'll say the operator X is equal to a matrix. Okay. So even if we use it like that, you should remember at the back of your mind that this is only a representation of the operator. Okay. So for calculational purposes, it doesn't make a difference whether you write X, the operator, as a matrix. All right, because it will all work out. But you just have to remember that it is a representation of the operator in a particular basis. Okay? So you should remember that the operator is different from a representation of the operator. So there are n square matrix elements like this. Okay, so there's one easy way to enumerate these matrix elements. Sometimes we'll be using this. We have got the operator here. Let's list the base brass here, A1, A2. Okay, let's list the base gets here, A1, A2, etc. Okay, the others are also listed. Now it's easy to write down these matrix elements. The first element is A1 x A1. All right, bra A1 x get A1. So this is bra A1 x get A1. Right. Similarly, this would be bra A1 x get A2 because we are writing it below get A2. So you look at this point. This is the matrix element here is decided by bra A1 and get A2. Okay, bra A1 and get A2. So this would be bra A1 x get A2. Bra A1 x get A2. You see that here each of this base bra is combined with one of the base gets. Okay, so each of this base bra is combined with n base gets like this. Okay, so there will be n numbers in the first row, there will be n numbers in the second row, etc. That's why we get an n by n matrix with n square elements. Okay, so now we know how to represent an operator by a square matrix. Okay, we can also represent the Hermitian conjugate of that operator by a square matrix. The next question is, how are these matrices related? How are these matrices related? Okay, so you could think of this as the basic definition of the Hermitian conjugate. Okay, this says that bra A double prime x get A prime is equal to bra A prime x dagger get A double prime star. Okay, you could remember it like this. Suppose we have this matrix element x A double prime, sorry, bra A double prime x get A prime. Okay, and if you need to find the complex conjugate of this, if you need to find the complex conjugate of a number like this, there are two things you must do. One thing is that you have to interchange this bra and get. So instead of this bra A double prime here, we should write bra A prime. Right, this should be brought to this side, and this has to be brought to the other side. Right, and write as the corresponding get. So this has to be done. Okay, the first thing is to interchange the bra and the get. All right, and then you also need to do one more thing. You should write x dagger here. Right, so x dagger can be defined as that operator which satisfies this relation. Right, so if you need to find the complex conjugate of this number, you should do two things. You have to interchange the bra and the get, and you have to replace x by x dagger. Okay, you could think of this as the definition for X dagger. All right. So we see that A prime X dagger A double prime is equal to A double prime X A prime star. Okay, so to get the matrix corresponding to X dagger, you have to take the matrix corresponding to X. All right. You see that the rows and columns have been interchanged. We said that this is the row index, this is the column index. Here, this is the row index, and this is the column index. All right. So to get from the matrix, to go from the matrix that represents X to the matrix that represents X dagger, you should do two things. You should change the row and the column. Okay, you have to interchange the row and the column. Okay, just as we said here, we have to interchange the bar and the ket. Okay, so when you go to matrix representation, this means that you have to interchange row and column. What does that mean? You have to take the transpose. So if you are making the row index into a column index and column index into a row index, then that amounts to taking the transpose of the matrix. All right. So you see here that from this we see that the matrix that represents X dagger is the transpose conjugate of the matrix that represents X. It's a transpose conjugate of the matrix that represents X. Okay. So if you have the matrix that represents X, okay, in order to get X dagger, you should do two things. All right. You should transpose the matrix X, to transpose the matrix X, and then complex conjugate each element in it. Okay, it doesn't matter which one you do first. First you can transpose and then take the complex conjugate, or you can take the complex conjugate of each element and then take the transpose. It doesn't matter which. Okay, so in the case of matrices, I think you might have already studied this in the case of matrices. A Hermitian conjugate of a matrix X, all right, Hermitian let's say that there are matrix, the Hermitian conjugate of a matrix X is obtained by taking the transpose conjugate. Okay, so X dagger is equal to X transpose conjugate. Okay, this is a matrix here. Okay, I hope this is clear. So the Hermitian adjoint operation has now been related to the concept of complex conjugate transposed. So when we are talking about matrices, the Hermitian adjoint of a matrix, okay, or of a matrix representing an operator, is obtained by uh, taking the complex conjugate transposed. Okay, so that's the relation between the matrix that represents X and the matrix that represents X dagger, right? One is the complex conjugate transpose of the other. Okay. Now, if an operator B is Hermitian, Hermitian means B dagger is equal to B. Okay. In that case, let's look at this matrix element. Bra A double prime, B, ket A prime, and let's find the complex conjugate of this. Okay, we know the steps to find the complex conjugate of a number constructed like this. You have to interchange the bra and the ket. So this becomes bra A prime and ket A double prime. Okay, one more thing I have to do is that I have to put a B dagger here. Okay, B has to be replaced by B dagger, but since B dagger is equal to B, I can simply write it like this. Okay, so in order to get the complex conjugate of a Hermitian of a matrix that represents a Hermitian operator, if in order to get the complex conjugate of a matrix that represents a Hermitian conjugate, you just transpose that matrix, right? So in order to get the complex conjugate, the only thing I need to do is to interchange the row index and the column index. Okay, so if B is a Hermitian matrix, then B dagger, all right, or B star, the elements, the complex conjugate of the elements is obtained by simply transposing the matrix. Okay, this is the definition for a Hermitian matrix. Right, that's the same thing that we see here. Right, if you want to find the complex conjugate of a matrix of a matrix that represents an operator, you simply interchange the row and the column. Okay, in other words, you take the transpose. Right, so if you this means that if I take the complex conjugate on both sides of this means that the matrix B is equal to matrix B transpose conjugate. In other words, B dagger is equal to B. Okay, so for Hermitian matrix, if I take the Hermitian adjoint, the matrix does not change. You get exactly the same matrix. Okay, B dagger is equal to B. So here I have used the square bracket to denote a matrix. Okay, to what is a distinguish between the matrix and the operator. So this is a matrix representing B, and if I take B dagger, I'll get B. Or in other words, if I take B star, I'll get B transpose. Okay, so you can think of either of this as the definition for a Hermitian operator. Okay, we saw that we can represent an operator by a square matrix. All right, the matrix elements are of the form bra a double prime x get a prime. Right, we said that this can be thought of as the row index and this as the column index. Right, now maybe it's more convenient, sometimes it's convenient or it's easy to understand if we denote it like this: x a double prime a prime. Okay, so this means that this is the a double prime a prime element of a matrix that represents operator x. So if I use an expression like this, you should understand that this is the a double prime a prime element of a matrix. Which matrix? The matrix that represents operator x. All right, so if I write x and then x with indices, this means that these are the matrix elements. Okay, matrix elements of the operator x. All right, sorry, matrix elements of the matrix that represents operator x. All right, so I'm being very precise with the language here, and as we go on, we won't be so careful about the language. All right, we'll say that these are the matrix elements of the operator. All right, but for now I shall be precise and I shall say that these are the matrix elements of a matrix that represents the operator x. All right. Okay, now with that notation, let's look at operator multiplication. Right. So we say that the way we arranged bra a double prime x a prime into a square matrix is in conformity with the usual rule of matrix multiplication. Right. Now, what's our usual rule of matrix multiplication? Suppose we have two matrices A and B. All right, and let C be equal to the product of these matrices. Okay, C is equal to AB. Okay, now the rule of matrix multiplication says that the ijth element of the product of these matrices, all right, or Cij, these are the, because it's a square matrix or because it's a matrix, or because it's a square matrix, we have two indices, all right, one row index and another column index. All right, so the Cij, the ijth element of C is equal to Aik. There's a sum over k. So this is Aik Bkj. Right. So this is the rule, usual rule for matrix multiplication. The ijth element of the product of matrices can be written like this. It's sum over k Aik Bkj. All right. So here we have the column, the row index I that appears here. The column index j here, it appears here. Right. And k is summed over. K is summed over. All right. Now the same rule works for matrices that represent operators also. The same rule works for matrices that represent operators. So let's understand how this works. We can see that this is correct. Let's look at a product of two operators x and y. And the product of these operators, let's write as z. So let z is equal to xy. Z is an operator, x is an operator, y is another operator. All right. Now let's look at the matrix elements of the matrix that represents operator z. So I can write bra a double prime z get a prime is equal to, okay, this is bra a double prime. So z is equal to xy get a prime. All right. Now what I do is that again, as we have learned to do, what we'll do is that we'll introduce an identity operator here. Right? I'll introduce an identity operator here. So I'll introduce an identity operator of this form. 1 is equal to, or identity operator is equal to sum over a triple prime get a triple prime bra a triple prime. All right. So this is the identity operator that I'm going to insert here. Okay. So that says that bra a double prime z get a prime is equal to bra a double prime. So I'll put the summation outside. Okay, sum over a triple prime. The summation I shall put outside. It doesn't matter. I could put it here, but then I can pull the summation outside because the summation is only over a triple prime. All right, so I'll put the summation outside. Sum over a triple prime, bra a double prime, x, and then what do I have here? Get a triple prime, bra a triple prime, and then triple prime here, y, and then get a prime. Okay, so you look at this expression. I have just introduced an identity operator in between. Okay, so this is, let me write it clearly. So this is bra a double prime x, okay, get a double triple prime bra a triple prime. This comes from the identity operator, and then I've got y and then get a prime. All right. Okay, this is what I have written here. This is sum over a triple prime, bra a double prime, x, ket a triple prime, bra a triple prime, y a prime. What is this? This is part of the identity operator, right? The full identity operator comes with the summation. Okay, so the full identity operator is this. All right, I have just pulled out the summation. Now this expression says that the usual rule for matrix multiplication works also for matrices that represent operators. Why? Right, if you look at this, let's use this notation just to be clear. Okay, so this Z, the bra a double prime Z a prime is the a double prime a prime element of a matrix that represents operator Z. So let me write this as Z a double prime a prime. This is equal to sum over a triple prime. Okay, what do I have here? This is x a double prime a triple prime, and then y a triple prime a prime. Okay, so this is exactly the same as the matrix multiplication rule that we have given here. Right, so instead of I here, I have got a instead of I have got this a double prime here. Instead of j, I've got a prime here. All right, and instead of sum over k, I've got sum over a triple prime, and the k index, all right, k index is summed over. Similarly, the a triple prime index is summed over. Okay, this is the row index and this is the column index of the product matrix. Right, so it works. So we have seen that the matrix, the way we arranged these elements into a square matrix is actually in conformity with the usual rule of matrix multiplication, right? So if you want to represent a product of two operators, you can write it or we can represent it as a product of two matrices. Okay, so our representation works in that way. All right. Okay. Now, what have we seen so far? Let me just summarize the matrix representation of operators. All right, I'll just summarize the matrix multiplication of operators. Okay, what have we seen so far? We saw that the base vectors that we use or bases are always in quantum mechanics. All right, always we use bases which are the eigenkets of a Hermitian operator. The eigenkets of a Hermitian operator. Now, this choice we could choose different base, all right? We could choose the eigenkets of operator A or operator B or operator C, okay? As long as these are Hermitian operators, all right? Now, once we choose the base, once we choose the basis, all right? Once we choose the basis, then we can represent an operator by a square matrix. We can represent the operator by a square matrix in this basis, all right? Now, if you go to another basis, the square matrix also will change. Right, the square matrix also will change. That's why we use this symbol. This means is represented by. So operator X is represented by a square matrix. Right, and in order to do this, we made use of this identity or the completeness relation. Identity operator is equal to sum over a prime, get a prime, bra a prime. Okay, we made use of this identity. So whenever we got stuck, we just introduced a one. Right. So in this case, when we started, all right, what we did was that we introduced a one here and here, or an identity operator on both sides. All right. That's how we learned that we could represent the operator as a matrix. All right. Actually, that's all we have done, and we saw that this is in conformity with the usual rules of matrix multiplication. Right. This matrix representation is actually in conformity with the usual rules of matrix multiplication. Okay. Again, all we have done is to insert the identity operator between x and y. This is an exclamation mark. This exclamation mark tells us how important this completeness relation is. Right? So by just inserting this completeness relation or the identity operator in this form, just by inserting it in different places, we are actually extracting some numbers that we can look at. All right? We are extracting some numbers that we can actually look at. All right? So we can represent uh, what do you say, operators by square matrices. Now, this is a good time to conclude. In the next session, we'll discuss the matrix representation of bras and kets. Okay. So in this session, we only saw that operators can be represented as square matrices. All right. In the next class, we'll see that kets and bras also have matrix representations. We'll see that kets can be represented by column matrices and bras can be represented by row matrices. All right. So that will complete the kind of matrix that will complete our matrix representation idea. All right. So if we can represent kets, bras, and operators as matrices, we can write all of quantum mechanics, all right, the rules of quantum mechanics in terms of matrices, right, in terms of matrices. So that is for the next class. Thank you.